Hi there, welcome to Geography 3075. Today we're going to talk about global environmental change, and I'm going to narrate this as a video just to get more high tech. So what is global environmental change? Well, the World Health Organization defines global environmental change as large-scale global environmental hazards to human health. And certainly we're going through a significant and unprecedented issue right now with COVID-19, but these could also be things like flooding or large impacts to our atmosphere, which could affect our health, the quality of our life, skin health, and so on. So why might we be concerned with these hazards? Well, as we've seen in the last couple of weeks, these hazards can affect our global economy. They can create conflict, and they can also eventually potentially create wars. So there are many different life supporting systems that we depend on, and our systems require that we have some stability in these life supporting systems. So as you've seen, any instability that can occur can affect the production and cultivation of food. It can affect our soil and the maintenance of our soil productivity. Water and the cycling of water, including where we get our water from and the availability of water for sustaining human populations. Plant resources, including crops and forests. So crops are an important natural resource for our food system, and forests helps us sustain our building, pulp and paper industries, and so on. Terrestrial, aquatic, and marine ecosystems are extremely important for food sources and other ecosystem services. So when we think of environmental changes and hazards to human health, we often think of climate change, but really climate change isn't the biggest hazard to human health. Certainly, we're also impacting land use and land cover change. We're changing land covers so quickly that we're disrupting the biophysical systems and reducing the ecosystem services of these systems to support human and other life. And when we change ecosystems on a large scale, we can also influence our weather systems through changing albedo, changing fluxes to the atmosphere. We alter temperature, which can impact how our crops grow. We reduce habitat continuity, so the ecosystem services in large patches of land cover type as opposed to highly fragmented land covers. And finally, we also affect our organic and inorganic pollution creation. So when we pollute the atmosphere and our waters, then we're taking this up, we're breathing it in, and we're affecting how our health is. So other hazards to our health include carbon dioxide in the atmosphere, and certainly we emit a lot of carbon dioxide through greenhouse gas burning, but natural systems also emit carbon dioxide as well, but not to the same level that we emit through burning fossil fuels. Temperature, including air and ocean surface temperature, has a big impact on our biophysical systems. And if they impact our biophysical systems, then this changes the ecosystem services that we derive from them. Biologically available nitrogen. So typically plants can't fix natural nitrogen, only certain types of legumes can. So when we put more nitrogen into the environment, we're altering these biophysical systems. Stratospheric ozone depletion. So stratospheric ozone depletion it's still occurring, but it's not occurring to the same level as we have had in the past because we've altered our methodologies of emitting stratosphere ozone, CFCs. So even though this is reducing, this is still a potential issue for us because it affects the amount of light that is coming through and the energy of that light, which causes us to burn. Changes in precipitation regimes. So we can have both extreme weather events, which would cause a lot of precipitation to fall at once and then run off, but also increased variability of precipitation events, such that you have big extremes in droughts, but also big extremes in the amount of rain that actually falls. Okay, and then through this, we also have changes in our hydrological systems and the supply of fresh water. So these changes in hydrological systems can affect, where precipitation actually falls and how that, the downstream effects of that. So how we get our water and how we use it. So other hazards also include habitat fragmentation. So when you disturb the different habitats, which are typically continuous, then you fragment these, and this can affect a variety of wildlife and plant biodiversity. Change land use intensification, which means the intensified use of land, such as agricultural land, and changes in ecosystems due to the loss of biodiversity. So when you're planting monocultures, you're reducing the biodiversity which exists within the landscape. In addition to these, land degradation, so the slow degradation of land, especially in agricultural areas, but also in forest lands as well. When you use them, you're kind of using up all the nutrients, so you're degrading the soils. Urbanization can encroach into very productive natural land, which can, or even also agricultural land, which can degrade the landscape, and also stresses on food producing systems. So any kind of intensification of food producing systems adds more and more stress onto the land. So how might any of these affect the stability of the biosphere's life-supporting systems? Well, when we consider all of these together, we apply an Earth system science approach to looking at these. So you can imagine that these are very complex systems, which when they are combined or looked at cumulatively, they can have multiple effects that span the range of all different types of biospheric flora and fauna, all the way to up to us. Okay, so when we manage these hazards, we need to adjust our strategies to account for global environmental changes. These changes are not only affecting our local ecosystems, but we're also affecting the global environment, and so this can have significant knock-on effects. For example, financial and government agencies increasingly need to manage their policies to account for global environmental change. And what's going on right now is really quite an interesting dynamic that we're seeing, where we're seeing knock-on effects between countries across the globe and this current coronavirus. Other impacts that have occurred, or other hazards that have occurred in the recent past, include the 1998 ice storm in eastern Canada, which cost more than $5 billion, and basically this caused people to have to stay indoors for about 2 weeks. Some of those people didn't even have power for 2 weeks, so you can imagine that that was quite difficult. In June 2013, the flooding of southern Alberta cost about $6 billion. Flooding in Toronto during that same summer was $1.2 billion. And of course, in May 2016, the Fort McMurray or Horse River wildfire cost more than $9 billion when you take all of the cumulative impacts together. So these hazards are having significant impacts on our Canadian economy, but if we kind of transpose these impacts globally, they can also have global influences. But of course, these are not just climate-related influences. There are other big impacts that we're seeing as well. Certainly, coronavirus is not related to climate, but we're seeing the global impacts of this very, very quickly. So really, we can no longer depend on this idea of stationarity, or the past is what's going to happen in the future. Things change, and we have to be able to deal with these changes. So this lecture for now is going to focus on climate change. I want to also mention that I'm going to introduce a reading to you at the end of the lecture that I'd like you to look at. And I'm going to set up a Zoom lecture for next Tuesday, so stay tuned for that. This should be kind of neat to hopefully have as many people as can possibly attend, and then we can talk about what's going on right now. But for now, we're going to talk about climate change and some of these underlying principles that have been understood for decades. Okay, so the physics of global climate change has been known for quite some time. All the way back to 1824, Joseph Fourier calculated that the amount of energy that was going into the Earth's atmosphere was making the Earth's atmosphere warmer than expected. And this is based on quite simple physics, that this Earth's surface re-emits infrared radiation. So the more radiation that gets through and is absorbed by the Earth's atmosphere, the more radiation kind of gets blocked in there, and that the atmosphere does not transmit infrared very effectively. So this warming of the atmosphere is, even if we're not observing it, we can predict that this is going to happen. In 1837, Louis Agassiz speculated that the Earth's climate could vary, and Svante Arrhenius in 1898 calculated that a doubling of CO2 in the atmosphere would increase the Earth's temperature by 5 to 6 degrees Celsius. However, he also thought that any increased warming of the Earth's atmosphere would be slow and beneficial to us. So interestingly, in the 1960s, it was research done by the oil and gas industry that really improved our understanding of global climate change. But because of a few lobbyists, this understanding was actually hid from the public. So it's interesting that oil and gas scientists were some of the first discoverers of the impacts of burning of fossil fuels on the atmosphere. So how much is the planet heating on average? Generally, it's been 0.6 degrees Celsius over the last century. And while that is fairly well known, the science of climate change is still quite complex and uncertain. If you hear ringing, I've got my dog beside me and he keeps scratching himself. So the science of climate change is still fairly complex, even though the physics are simple. The complexity occurs because we do not understand the significance of the changes that we are seeing over the Earth's surface. And so this requires a knowledge about science and society. So all of the feedbacks that we're seeing, these are complex systems. And so we have to continue to understand how these feedbacks affect other cycles on the Earth's surface and in oceans. So just a quick overview. This is probably something that you've been learning since about grade 3. Basically, the sun's radiation comes in through the atmosphere. That radiation hits the ground surface here. I'm going to circle it. Hits the Earth's surface. That radiation is absorbed and then re-emitted as infrared radiation, which is then trapped by some of the greenhouse gases in the atmosphere, while other parts of that radiation is irradiated back into outer space. So any of that infrared that is trapped by the gases in the air is trapped and reabsorbed and then re-emitted as heat energy. So when we think of greenhouse gases, we often think of carbon dioxide and methane. Oh, here's Finn. We often think of carbon dioxide and methane, but really there are many different greenhouse gases that are available, and these are highly variable through the atmosphere, and they also vary in time in their concentration. So these gases are able to absorb and re-emit infrared radiation, and their degree of emission of radiation also varies. So some gases such as methane have a very significant atmospheric forcing, which means that they produce a lot of heat energy, when they absorb radiation, whereas other greenhouse gases such as carbon dioxide are not as potent. In addition to this, we also consider the amount of greenhouse gases in the atmosphere. So water varies between 36 and 70%. Concentration, CO2 is between 9 and 26%, methane 4 and 9%, ozone 3 and 7%. But depending on their forcing or their ability to convert light energy into thermal energy, these can be more potent. In addition to this, we also consider the amount of time that these molecules spend in the atmosphere. And this is what we call the residence time. So methane is very potent, but only has a very short residence time in the atmosphere, whereas carbon dioxide has a long residence time of up to between 50 and 100 years. So even though carbon dioxide is not as potent as methane is for converting energy into infrared energy or thermal heat, they exist in the atmosphere for a lot longer, so can have a significant impact. Most gases, any greenhouse gases that have basically 2 or more atoms, are greenhouse gases. Okay, so in addition to this, we need to also consider that as we change land cover types, we also influence the amount of greenhouse gases, and especially carbon dioxide, within the atmosphere. And in about 1956, David Keeling started measuring greenhouse gases at Mauna Loa in Hawaii, and he measured the carbon dioxide concentrations at this particular location from about 1960 to the present. And what he discovered was that carbon dioxide levels were increasing over time. You can see the curve to the right there. But also that the seasons have a significant influence on CO2 variability globally. So as you can see, the carbon dioxide concentrations declining over time. This is related to the green up and absorption or sequestration of CO2 by northern hemisphere forests. And then as CO2 levels peak in winter, this is due to the burning of fossil fuels. So a lot of this variability can also be related to some of our climate patterns at a particular year, or weather patterns in a particular year, but also how we change or have significant impacts or changes to these land cover types. Okay, I'm not going to show you this animation, but it's really interesting. If you click on the link, it's difficult for me to show here, but if you click on the link, you can see how all of the influences impacts global air temperature. So this is not only just greenhouse gases from fossil fuel emissions, but also changes in the Earth's rotation, changes in solar output, volcanic eruptions, and so on. It's kind of a neat graphic. Okay, so as mentioned before, the science of climate change is complex and uncertain. Even though we understand the physics quite well, these underlying feedback mechanisms are also uncertain, and so scientists are naturally cautious. And even with our predictions of how the climate has been changing in the past to now, we've always had scientists have typically had a cautious approach, and in fact the climate is changing more than scientists have, more and more rapidly than scientists actually have predicted. Okay, so there are many uncertainties in these feedback loops, and some of the biggest uncertainties are associated with the sensitivity of feedbacks. Even though we've performed many experiments, and we know that carbon dioxide traps heat, it's these feedbacks that create the uncertainties in our ability to predict how the climate is going to change in the future. So a couple of simple feedbacks here. The positive feedback, which I'll circle here. This is a fairly simple one where increased warming will cause ice to melt in the Arctic. This can decrease the albedo of the ocean such that the albedo is able to absorb more radiation. More radiation that's absorbed causes the ocean to warm up, and that increases overall the air temperature. So a negative feedback or an opposite to feedback to this could be increased warming of the atmosphere causes increased erosion of rock materials, which puts more carbon dioxide, it increases the weathering of these rock materials. It puts more carbon dioxide into the rock, which eventually causes the cooling of the atmosphere. So we're not clear on how these feedbacks will intensify warming. Also, some of the feedbacks can offset each other. So if you have a positive and a negative feedback occurring at the same time, we don't know which feedback is going to be stronger or how these are going to offset each other. There's a range of possibilities, but we're not able to provide absolute predictions. But what I can say is that our general story is correct, so that the atmosphere is warming, and that this is going to have global knock-on effects, but we don't know, the timing or the magnitude of these impacts. So climate change model predictions provide us with a range of scenarios or predictions. So whenever you see these climate change graphs where you're seeing the increased air temperatures over time, and you see the error bars associated with them, these error bars are due to a variety of predictions of how we think that the environment is going to respond. So the historic trends to now are amazingly accurate, but the interannual variability is complex. Predicting the future is difficult, but if the past is a predictor of the future, then these models are really actually doing a great job. Okay, so here is some model predictions. This is the period of high certainty. So this is when we were able to, actually I can highlight it here. This is the period of high certainty right along here. This is the period where we've been able to measure our climate. We've been able to measure the amount of precipitation and the air temperature over time since about 1950 to now, and we'll continue to do that. And each of these different lines represent a prediction based on a model scenario. And this is based on how we think these feedback mechanisms are going to interact with each other. Okay, and certainly maybe we're following this kind of general trend upwards over time. So some models, such as the CCSR model, is kind of like a worst case scenario or business as usual, whereas kind of the bluer models here, I'll highlight along here, are kind of like a best case scenario. So how we can really reduce our emissions over time. So the lowest emissions scenario. Okay, so in addition to this, we know that the world's been warming. Each of the previous decades have been warmer than the decades prior to these. And I'll show you this map here. This is a map of annual air temperatures from 2008 to 2013. And this is the difference or the anomaly from what it was in the past from 1951 to 1980. So you can see, so anything that's kind of white here shows that the climate hasn't changed between 2008 and 2013 versus 1951 to 1980. But anything that is in yellow to red colors indicates that the climate has changed by up to 4 degrees, which is quite substantial. Anything that's in gray basically indicates that I think that must indicate that there's been an actual negative change. I was wondering if there was no data there, or anything in light blue here has been, up to a 1 degree cooling. So we can see that the whole world is changing. We can see that it's a lot warmer than it has been in previous decades. And this is not a model. This is actual measured data. These are measured using atmospheric weather stations, air temperature measurements, as well as air temperature and sea surface temperature measured on buoys. In this one in particular, it wouldn't include sea surface temperature because it's just the atmospheric temperature, but the ocean buoys can also measure sea surface temperature to determine how the oceans have been changing. Greenhouse gas emissions have also been rising, so these are higher than the last 800,000 years due to population growth and due to urbanization and mechanization, as shown by the Keeling curve. But we can also look at changes in greenhouse gases within ice cores, and so this gives us a paleo record of how these systems have been changing. So what are the impacts of these changes on natural resources? And so this is where kind of we're taking climatology and bringing this into the framework of this course. So certainly if we get changes in water, changes in the location of where precipitation falls and our water availability, then we're going to change agriculture, what is able to grow where, and the northward movement of agriculture as well. But we're also changing some of these biophysical systems. Okay, in addition to this, we have significant increases in ocean acidification and impacts to the food chain. So this is another area that we have to consider as well. And this is globally relevant impacts to food availability. So where's most of the global warming going? So what is the biggest impact on the different Earth systems? Well, most of the impact occurs within the ocean. 93.4% of the effects of global warming affect the ocean. The ocean is an enormous heat sink, so any of that warming temperature is going to go straight into that, into heating up the ocean. But as you know, the heat capacity of water is very different from the heat capacity of air. So the water can absorb a lot of energy before it actually changes temperature. The atmosphere is affected as well. 2.3% of how the atmosphere is changing is actually remaining in the atmosphere. Continents to a lesser degree, and then you have lower impacts to glaciers and ice caps, Arctic sea ice, Greenland ice sheet, and so on. So even though these systems are changing quite rapidly, most of the energy goes into the ocean. These can have significant impacts on ocean currents and the movement of ocean currents. For example, when sea ice melts, it puts cold, fresh water on the top of the ocean, which can dampen and force ocean currents downwards into the deeper ocean. It affects water temperature and surface. At the surface, it can affect water chemistry and increase the acidification of the ocean as well. Okay, so as mentioned, the heat capacity of water is much higher than air, and the density of water is about 800 times that of air as well. So it takes about 4,200 times more energy to heat up the same volume of water as it does to heat up the same volume of air. So you can see here on these maps the spatial patterning of surface ocean temperatures warming up over time. And this is compared to, so this is like an anomaly compared similar to the last map, where you're looking at basically the patterns from about 1950 to 1980 compared to the current patterns, and you're subtracting them. So anything that shows a red is basically an increased warming compared to the way it was in the past, whereas everything that's in blue is actually showing a cooling. But you can see here that the greatest warming is occurring along the equatorial region, especially associated with changes in atmospheric currents and a dampening of the changes in oceanic currents and a dampening of the oceanic currents, especially at the polar regions due to sea ice melt and this kind of pushing down or dampening of the currents in the north. So the graph on the bottom illustrates this as well, showing average global sea surface temperatures. And you can see for the period up to about 1940, and a little bit from the 40s through the 50s and 60s, that ocean temperatures were significantly cooler than they are today. And we're basically seeing increased warming of these ocean sea surface temperatures over time, which illustrates just how much of that energy is actually going into the ocean, into ocean waters, especially at the surface. Okay, other evidence that related to climate change. So we've seen that glaciers have had significant reductions since the 1980s. So you can see these are from the 1970s. These are all the areas that where mountain glaciers have thinned over time, from yellows to red, and in a few areas where you've seen glacial growth. There's one here in Canada, and there's a couple in Norway, or a few in Norway here. These could be associated with certain atmospheric anomalies that are occurring just in those areas. Reduced snow cover has been documented as well, such that you get in earlier spring melting of ice on rivers and lakes. When you have reduced snow cover and earlier spring melt, you actually increase the season, the warm season, for other cryospheric processes such as permafrost thaw. So permafrost is greatly affected by snow cover. If you reduce the amount of snow cover, then the permafrost is exposed to a warmer atmosphere, which causes it to thaw even more rapidly. And permafrost covers about 40% of Canada, so this rapid thaw of permafrost is quite concerning as well. We're also seeing significant declines in the area of sea ice loss, especially in the fall. And this sea ice loss in the fall, when you have some solar radiation that's still being absorbed by ocean, can accelerate the positive ice and ocean warming feedback. So what are some of the impacts on natural resources? This albedo, ocean warming, and runaway greenhouse effect, certainly there's some big impacts there, as well as increased fire seasons. There are impacts to forestry, but also impacts to human health, especially when you're breathing in some of these particulates and pollutions associated with fire season. Okay, as I mentioned, changes in permafrost temperature, so warming and thawing. As soon as you get you shorten that cold period, we're also seeing kind of a shift in the snow cover season to later in the fall as well, or sorry, to earlier in the fall as well, such that when snow falls on permafrost, basically it doesn't allow the permafrost in winter to be exposed to the cold atmosphere. So if you have earlier snowfall in the fall, then the atmosphere is still fairly warm. The permafrost isn't exposed to cold winter temperatures. And then if this is compounded by an earlier spring melt, which exposes the permafrost to warmer spring temperatures and a longer thaw season. So in addition to this, changing permafrost has stored vast amounts of carbon since the last ice age, so about 10,000 years. And as this permafrost thaws, it starts to emit carbon dioxide and methane in addition to its thaw. So in 2008, Lenton determined that permafrost could be a potential tipping point mechanism for the global climate system, which means that once permafrost starts to thaw and it starts to emit carbon into the atmosphere, then this can accelerate this this global carbon climate cycle, positive feedback. Okay, some of the impacts on natural resources of permafrost thaw. Well, this can include changing water resources, flooding, because permafrost is basically frozen ground, and so it contains a lot of water. When permafrost thaw, it can cause a rush of water to go through wetlands to river systems, which causes flooding. It can also alter habitats for certain species of wildlife, which affects hunting and the availability of country foods, especially in the north. And one thing that I thought was interesting, I was talking to someone up north, and they said, well, when you get the alteration of these country foods, it means that people can no longer hunt in the areas where they used to hunt, which means that they have to rely on grocery stores to get a lot of their food. And I don't know if you've ever been up north into the Northwest Territories, Yukon Territories, Nunavut, but the reliance on grocery store food is very expensive. It's very costly for these people, and often they can't afford this. So this creates a significant food security issue. Okay, just a little example of some of the changes that are occurring in permafrost, and this is some of my own research. I'm very interested in permafrost, and this photograph illustrates kind of the edge between the permafrost and the wetland environment. And you can see this edge that kind of comes along here, and it scoops in this way and then back again. The edge of the permafrost is basically where you have all these trees dying because the soils are waterlogged. All the water that comes from the thawing of the permafrost basically accumulates in this wetland environment here to the left of that red curve there. All the permafrost is on the right here, and these are manifested, especially in the southern part of the Northwest Territories and in the Yukon, as these kind of permafrost plateaus. They're slightly upraised, which allows trees to grow on them because the trees are separated from the water or the saturated hydraulic conditions. Okay, when permafrost starts to thaw and these wetlands start to open up, more radiation hits the stems of the trees, and this is a thermal infrared photograph of radiation hitting the trees. And anything that's kind of white to red and into yellow, these are the warmer surfaces, up to 13.9 degrees in this case. Anything that's blue or dark blue illustrates colder surfaces, down to minus 0.8 degrees Celsius. So here you can see this heat energy from the sun hitting the tree stems, and then this energy radiates down the tree stems into the permafrost, which causes it to thaw out even more quickly. So this is just further to this study. We looked at mapping permafrost thaw over time from about 1970 to 2015, and indeed we've been mapping it since then as well. We did another data collection in 2018 using LiDAR data. So this is a combination of satellite imagery and LiDAR, and over time we can see this acceleration in the thaw of permafrost with kind of a tipping point that occurred around 1997, and that tipping point, or that threshold shift that caused the permafrost to thaw even more rapidly, was associated with an atmospheric warming event, a severe El Nino, which warmed up this whole area and caused the permafrost to thaw even more quickly, which caused more water to run off, and then that water heated up the permafrost, as it went by, and caused that permafrost to more rapidly thaw. So typically we don't see these types of threshold shifts in the environment, but certainly we saw it in this case in this big watershed. Okay, so this is just to show you how the ground surface elevation changed over time. So the red to yellow to green areas, these are all permafrost plateaus illustrated by a LiDAR digital elevation model. And in the center here, the blues and turquoise, this is a large fen wetland. And if you take a look closely, I'm going to show how the ground surface elevation has changed over time. You can see that there's shifts in the biggest shifts in the ground surface elevation occur within these circled areas. So I'll show you how that changed over time. Just that. Okay. So I can't shift back and forth, unfortunately. This doesn't allow me to do that, but you can definitely see a big change in that permafrost. Okay, other evidence related to climate change. We've observed a mean sea level increase of 0.19 meters on average since 1901. So this is the post-glacial sea level rise over time in thousands of years ago. So this is our current time here, and we're seeing kind of a gradual increase in the sea level rise, especially associated with thawing ice sheets, but most recently this is due to the ice shelves retreating and falling into the ocean. So what are the impacts that this has on natural resources? Well, it can impact coastal cities and coastal agriculture. It has a significant impact on climate as well, and why our precipitation falls. More locally, it affects fisheries, and it also affects local wetlands such as mangroves and their ability to buffer against major storm surges. Okay, some of the additional evidence of global climate environmental change. We're seeing significant impacts of global environmental change on our ecological system. So this is starting to get into some of our natural resources. How does this affect our ecosystem processes? Well, we've seen an increase in average temperature, which can affect the frequency and extreme variability of weather events. And if you have increased, say, drought, we can have increased fires, but we can also we're also observing increased storms, which can affect ecosystem function. We're seeing differences in the amount of precipitation over time and where precipitation falls. We're seeing episodes of cold weather in some areas, even though we expect these to decrease over time. So globally, we're seeing an increase in the number of frost-free days. And we're also seeing a change in the growing season. So in some places, the climate is causing some areas to not be appropriate or suitable for agriculture anymore. Whereas in other areas, we're seeing shifts in the growing season such that some places can grow more crops when they haven't been able to previously. Okay, so within ecological systems, we'll also have winners and losers. So some species might benefit from the increased temperature of oceans or the atmosphere. They might benefit from chemical interactions or differences in pH and so on. Okay, for example, nitrogen-fixing cyanobacteria in the ocean are going to benefit over other species because of increased temperatures. Cyanobacteria favors increased ocean temperatures over other species. So what I want you to do is I want you to think about some of the consequences that this might have, where you have differences or winners and losers in these ecological systems, and how they might affect or create knock-on effects in the environment. So how is global ecological change affecting ecological systems? Well, it's expected that with more carbon dioxide and higher temperatures, then we'll see higher rates of plant growth because plants use carbon dioxide for photosynthesis. This is what's called the carbon dioxide fertilization effect. And I just wanted to show you this experiment, the FACE experiment in the photograph on the right. And what they're doing is they're enriching the atmosphere above these trees with carbon dioxide to the levels that they expect would occur in the future. And then they're looking at how the ecophysiological differences or changes in the trees and how they compare with trees under a normal CO2 atmosphere. So based on these experiments, what they found was that trees produce more carbon in their leaves because they took up more CO2. But they also found that the trees were limited by nitrogen and phosphorus, so they just didn't have enough of the nutrients that they required to continue to uptake the CO2. In addition to this, they found that insects were more prone to eat more leaf material, and that over time trees absorbed less carbon dioxide than expected, and they actually kind of grew less. They started to stabilize in the amount that they grew. Okay, so are rainforests resilient to global environmental changes? Well, it really depends on what their limitations are. So they increased fertilization of CO2 could increase tree growth, resulting in more storage of carbon. But at the same time, when you have more warming, then there's a risk that there will be stresses associated with water limitations. So if you have higher temperatures, then this means that trees require more water to grow because they're transpiring water that's falling on the ground. Now, a study by Flanagan et al. In 2016 demonstrated that for every degree of warming of air temperature in the boreal region in Canada, we also require a 15% increase in precipitation to fall in that area to maintain the same moisture levels that we have today. So in the case of rainforests, higher growth rates require more nutrients to grow as well. So when you combine the limitations from nutrients and the potential limitations from water, there can be it is believed that these trees will not grow as much. Hi, Finn. You want to see Finn? Here he is. So this, combined with other existing problems such as deforestation, fire, and overexploitation, really makes these rainforests at risk. Okay, so how can global environmental change disrupt interactions between species? Well, certainly plants and pollinators have co-evolved, and if there is a change in the climate or a change in the seasonality, then you're going to have one impacting the other as these changes occur. Here, the production of larvae coincides with the production of nectar from flowers, and we also have to remember that pollination is a keystone process. So both human managed ecosystems and natural terrestrial ecosystems depend on these. Also, flowering plants require pollinators to transfer pollen, and if you're changing these systems, then clearly we're going to have variations in the ability of these ecosystems to continue to thrive. Global environmental change also has significant impacts to our northern forests as well. Much of the change in air temperature is going to be most strongly felt in northern regions, as illustrated by the maps. In Western Canada, we've already experienced a 0.7 degrees Celsius change, and this actually matches a lot of the early published work based on climate change models as to how these ecosystems and how this environment is going to change. Some of the basic changes to forest biology and also the forest industry include increased rates of fires. If you have warmer temperatures, there are greater rates of evaporation, which causes a drying of the natural environment and more fuel development. Mountain pine beetle outbreaks with less severe winter temperatures, as we've read in one of the previous readings. This is going to cause this will continue the mountain pine beetle outbreaks that are occurring across BC and central to northern Alberta. In addition to this, when mountain pine beetle infest forests, those forests eventually die, and then they create even larger sources of fuel for wildfire. Fungal outbreaks such as Dothostroma needle blight in British Columbia occurs due to wetter and warmer winters as well. And then we have also reforestation failures because of drought. So all of these together can have a significant impact on the forest industry. Some of the changes that are expected to occur in forests over time in British Columbia. So for example, we have mean annual air temperature and environmental and climatic zones for vegetation growth. And then we have the range of Douglas fir on the bottom. And you can see that over the next 100 years, we're going to see significant increases in air temperature, but also the movement of species north across valley systems, and especially also in mountainous areas as well. So under various climate change scenarios, we expect some of these species shifts to occur in the near future. One of the biggest areas that are likely to be impacted are the subboreal and montane zones, which will move outside of their climatic envelopes within the next 50 years. So some of this is related to snowpack and snow cover distribution, especially in high mountain environments where they're just not seeing the same amount of snow precipitation in those environments as they used to, so there's less water there. Okay, other influences include the movement of trees into new potential habitats. So some species are expected to expand in their ranges, such as Douglas fir, ponderosa pine, and other broadleaf vegetation species. With regards to commercial species, we're expecting that some of these high elevation or boreal species will lose some substantial portions of their habitat as well. With regards to habitat fragmentation, as soon as we fragment the landscape, this creates increased sensitivity to climatic variability, and it also reduces the resilience of some species of plants and animals. One example is this 99% loss of tallgrass prairie in the United States. In addition to this, we're also seeing significant losses of boreal system wetlands and also prairie wetlands as well, especially due to agriculture, although agricultural disturbance of wetlands has been declining since about the 1970s. Habitat area is also very important because this determines how many plant and animal species live within a patch and how large the populations are. So any kind of perturbation to the natural environment, especially on small areas, can drastically affect populations within these fragmented environments. Whereas if you have large undisturbed areas that are contiguous, then the populations can more easily readjust after any disturbance. Okay, in some cases, small population can be rescued by adjacent populations, which is what we call a rescue effect. Okay, with regards to riverine systems, these can be greatly affected by limitations in elevation and temperature. So if you have a change in one aquatic ecosystem, then you don't have the corridor with which species can move. The same occurs as well in terrestrial environment, where species may be limited by terrain-based attributes. So elevation, water temperature, water quality, and so on can be boundaries for the movement of species to different areas or corridors to different patches. Okay, as air temperature increases, it's also expected that the range of each population will decline, and this will make dispersal even more difficult. Okay, so some of the interactions between these ecosystems and the global feedbacks are very difficult to predict. You can see how if we have one kind of knock-on effect, how it can influence other systems locally, but also potentially globally as well. Scientists agree that it is wise to limit change to less than 2 degrees Celsius, but in many cases, even 2 degrees Celsius is a massive increase in average global air temperature, which we're not even there yet. The other concern is that these changes may be irreversible and could also be disastrous. So what are some of the global warming projections? One of the big groups that does a lot of this global warming modeling is the Met Office, the Hadley Center for Climate Change in the United Kingdom. And what they do is they apply not just atmospheric models, but they use an Earth system approach to develop the state-of-the-art of climate models. So they're looking at atmospheric changes in 4 dimensions, but they're also looking at oceanic changes as well. And they basically set up the Earth as kind of a 4-dimensional, 3-dimensional plus time grid-based approach. In addition to this, they also look at the impacts of land cover change and how these feed into the model as well. So when they run these models, they look back decades, but they also look forward decades as well. Okay. So based on these predictions, do you think we're in big trouble? Well, resources management faces a number of difficulties for future generations, and this is something that we can't hide. Also, as time goes on, the risks or the potential to lose something that is important to us becomes a lot worse in the long run. Even so, it is likely that the climate in 25 to 30 years from now is going to resemble what we have today, but it is going to get steadily warmer, and we're going to see greater impacts on our natural climate variability as well. So what can we expect to happen? Well, we can expect that heavier rains and drier in-between periods, so greater droughts, which could create more intense and widespread wildfires. We expect to see coastal flooding becoming more frequent and more intense, which is going to affect the coastal economies and people living along the coast. Longer-term climate could destabilize governments because people are starting to compete for resources, and it could increase conflict and the potential for war and political instability. We don't really know when this is going to happen. It could happen in tens of years, hundreds of years, or even 1,000 years. But certainly just the most recent COVID-19 outbreak has completely just destabilized the global economy within 2 to 3 months. So that's quite amazing. I'm sure you've seen this graph before. Trends in costs of natural disasters in the billions of US dollars have also increased over time. But what you'll notice here is that geophysical events such as earthquakes, tsunamis, and volcanic eruptions, which are not affected by climate, have basically stayed relatively the same, which is what we would expect. Other events that are affected by climate, such as meteorological events, hydrological, and climatological events, have increased substantially over time, resulting in billions of dollars spent for each of these natural disasters. Can we be optimistic about our future, given that we know that the climate is changing and that the Earth ecosystems and our ecosystem services are also changing? Some people have a best case scenario for these changes that are occurring. Some of these best case scenarios could be that the Earth is less sensitive than currently believed. Plants and animals could adapt. Human societies could develop better political will and power. And we might also have technological breakthroughs which could reduce the impacts that we have on the global Earth system. So one thing that I'd like to stress to you is that the rate of change of our ecosystems over the last 30 years has been far more rapid than in the last 10,000 years, even though we know that ecosystems and climates have changed over millennia, over hundreds of thousands to millions of years. These changes that are occurring right now that we're forcing are greater than anything that we've ever seen. The other concern is that what if we're wrong? What if the Earth is actually more sensitive? We are already causing or creating chaos in various parts. So maybe this idea of this rosy outlook for the future isn't such a great idea. To end this topic, I'd like to have you read an article from EOS, which is out of the American Geophysical Union, and it's based on the future of what we think the carbon cycle will be in a changing climate. So if you could read the article, and if possible, I'd like to have a Zoom session with the class. That will be next Tuesday, so stay tuned for instructions. But basically, I'll send you a link, and then anyone who can connect should do so. It's not mandatory, so don't feel that you're losing marks if you don't connect. I know these are difficult times right now, but I think that it would be great to have a conversation on this. The questions that I would like you to answer are: how do we plan mitigation strategies for natural resources? What is the future for geographers, environmental scientists, agricultural sciences, etc.? Do you think that the current situation with COVID-19 will change how we view the environment and our reliance on the economy, or might we revert to a business as usual once this is done? Do you think that it would take a similar global catastrophe to change our perception of our place and our connection to the environment? So if you're not able to attend the Zoom lecture, and even if you can, I'd like you to answer these questions. I'm going to put together a folder on Moodle that you can drop your answers into on Monday or Tuesday. And then if we could get together to discuss this, as many of you as possible, that would be great. Okay, thanks very much. I hope you guys have a nice weekend, and I hope you're taking care. Okay, bye.